some examples of epitaxial quantum dots, the growth and the physics background, you can see on the left and in the middle two examples of ordered quantum dot arrays formed on a gallium arsenide 3-on-1b surface, single quantum dots and quantum dot molecules, and on the right side an example of application quantum dots, 1.55 micron indium phosphide telecom quantum dots. The growth modes for growing these quantum dots are shown on the bottom. We have three basic growth modes in the epitaxy, and the middle one, this Transit-Krastanov, is the one for the direct growth of quantum dots, which are formed by first forming a layer and then islands. The physics background is a change of the density of states from the bulk square root behavior to the singular quantum dot behavior. The growth is by molecular beam epitaxy. This is an ultra-high vacuum process using elemental sources of gallium, indium, nitrogen, and they are evaporated onto a heated substrate. On the left, you see a real image of a MBE machine, and on the right, the steam with the sources and the substrate in the center. Traditional applications of these quantum dots are optoelectronic devices, and here are examples which we did in the past of 1.55 micron indium arsenide indium phosphide quantum dot telecom lasers. On the top, a Fabry-Perot laser, deep etched, then a micro ring laser, mode-locked laser, and also an integrated extended cavity laser, all devices which are needed for the internet. But now let me come to the current research, and this is on indium gallium nitride nanostructures. I will present results on quantum dots and also on quantum wires, on nanowires, and applications are for lighting displays. I will concentrate here on hydrogen energy and biosensors. You can see on the left AFM images of quantum dots with different indium nitride deposition amounts, so they get different size and density. And on the right side, examples of indium gallium nitride nanowires. Let me start with solar hydrogen generation by photoelectrochemical water splitting using these indium gallium nitride quantum dot nanostructure photoelectrodes. This is the hydrogen energy cycle. Well, we start with sunlight, which shines on the electrode. This way, by photoelectrochemical processes, water is split into oxygen and hydrogen. The hydrogen is stored and then can be used on demand with hydrogen fuel cells to produce electricity to drive a car. And the only product or the only emission is water. So it's a fully carbon-free energy cycle. So how do we produce, how we fabricate the hydrogen? This is a scheme of the photoanode structure showing the quantum dots grown on an indium gallium nitride layer, in this case on a sapphire substrate. The electrochemical cell is completed by a platinum counter electrode. And I also show you here the reaction mechanism. Water is oxidized at the quantum dot anode to produce oxygen and is reduced at the platinum counter electrode where the hydrogen is produced. I come to the basic characterization of this type of photoelectrodes. The first important measurement is the photocurrent density versus voltage against the silver chloride reference electrode in this case. The structure are indium nitride quantum dots on an indium gallium nitride layer with 54% indium composition, and the illumination is by one sun. That means 100 milliwatts per square centimeter. Light power, white light. And from the photocurrent, we can deduce a solar to hydrogen efficiency of 6%, which is quite a high value. This is at 0. The only power input is sunlight. And then there is an applied bias to photon efficiency of 15%, where an extra voltage of 0.2 volt is applied. 15% at a applied voltage of 0.2. This is the real output power, excluding, of course, the electrical power which is input. The next important measure is the incident photon to current efficiency. This is the number of electrons produced by the number of monochromatic photons. It is plotted against the wavelengths of the excitation. Important point here is, because for indium gallium nitride, we can adjust the bandgap energy by the indium composition to the optimum value for absorption of the solar spectrum. So here, the peak of the incident photon to current efficiency coincides with a spectrum, with a peak in the spectrum of solar radiation. So we make full use of the sunlight in this case. The direct measurement of the hydrogen and oxygen generation is shown here. It is measured by gas chromatography. And again, we see that the hydrogen generation as a function of wavelengths, of excitation wavelengths, follows the incident photon to current efficiency. So again, we cover the peak of the solar spectrum. The ratio of hydrogen to oxygen gas evolution is 2:1. That shows us we have overall water splitting without side reactions. So the only reaction is the reduction and oxidation of water with the generation of hydrogen and oxygen. This presence or the non-presence of any side reactions is better shown in the Faradaic efficiency. And this compares the hydrogen evolution as a function of time, measured experimentally by gas phase chromatography and compared theoretically to the photocurrent. And we see we have a Faradaic efficiency of 94%, which means 100% efficiency within the experimental error. That shows all current we put in is indeed converted to the production of hydrogen. Stability and photoswitching behavior. The photoelectrode is very stable. Here on the left is a measurement at 0 voltage, measured in 2 electron configurations, so the real device only consisting of the quantum dot photoanode and the reference electrode. And the photoswitching follows the light on and off cycles instantaneously. So we have a very efficient and reactive photoelectrode here. Let me repeat again. The solar to hydrogen efficiency achieved here is 6%. And if we input a certain electrical power, the maximum applied bias to photon efficiency reaches 15% at 0.2 volt. And we observe no degradation of the photoanode. What is the secret now of the quantum dots to operate with such a superiority? The fact is, indium nitride has a very interesting surface property. It contains a very high density of positively charged surface donors to a density of 2 to 3 times 10 to 13. Because these donors sit on quantum dots, not enough electrons can enter the quantum dot, which has an atomic-like energy structure, due to the Pauli exclusion principle. So these positively charged surface donors cannot be screened. Electrons are expelled into the indium gallium nitride layer underneath. This creates a very strong electric dipole due to quantum effects, which actively attracts electrons. And this active attraction of electrons basically translates into catalytic oxidation enhancement. And this is the secret of the very high efficiency of the photoanode for the water splitting reaction. Other structures we have investigated include nanowalls and also nanowires. On the left SEM image, you can see example of nanowalls, and on the right, indium gallium nitride nanowires. This is the behavior of a nanowall photoelectrode. Again, on the left, the incident photon to current efficiency cover the solar spectrum, the peak of the solar spectrum, because optimum band gap. The efficiency now goes up to 9% at 0 voltage and to 25% at an external voltage of 0.2%. And again, the Faradaic efficiency is almost 100%, and we have a very high stability of this photoelectrode, well, because indium gallium nitride and indium nitride has a very high chemical stability. We have compared now compact layers, nanowalls, and nanowires, and it turns out the nanowalls are best, but all are quite comparable. So we have to take care here about the balance between the catalytic activity and the surface area. Of course, the surface area for nanowires is largest, but the surface catalytic activity of the nanowire sidewalls is not high. So nanowires here do not produce more hydrogen because of this critical balance. Nanowalls with slightly tilted sidewalls behave best. We have used nanowires as anti-reflection structure on pyramidal silicon. What we did is we etch a silicon substrate into pyramids. This is a well-known technology for enhancing the absorption in solar cells. And on this pyramidal silicon substrate, we grow indium gallium nitride nanowires, which is shown on the right. And this is a performance of this anti-reflection photoelectrode. Under chopped light illumination, the current versus the applied potential, and then the current versus time at an applied potential of 0.6 volt. And we can see the photocurrent is enhanced by about 200% due to the anti-reflection structure of this photoelectrode. And the direct measurement of the reflectivity shows that the nanowires on these pyramids have the lowest reflectivity. We did simulations shown at the bottom, and indeed, starting from a silicon substrate to the pyramidal edge, then nanowires on the planar substrate, and finally nanowire on the pyramids, the reflectivity continuously reduces down to 1.5% for the pyramids with nanowires. So this is a hierarchical anti-reflection structure taking advantage of the nanowire morphology and the pyramidal structure. With this, I would like to come to biosensors and ion sensors with indium gallium nitride quantum dot sensing electrodes. And we will see the underlying physics and the underlying principle both for the water splitting efficiency and also for the sensitivity of biosensors is the same. So there is a general underlying principle. This is an example of an indium gallium nitride quantum dot glucose biosensor. On the left is a potentiometric sensing setup. So we use potentiometric sensing instead of amperometric sensing. So we have the indium nitride quantum dot working electrode and then reference electrode immersed in the glucose solution. Then we show the biofunctionalized quantum dots. The quantum dots grown again on an indium gallium nitride layer on a sapphire substrate. The quantum dots are functionalized by an enzyme, in this case glucose oxidase, which leads to the catalytically enhanced oxidation of glucose. This oxidation, we will see, change the surface potential of the quantum dots, and this is then measured as voltage between the reference electrode and the sensing electrode. This is the first measurement on the sensitivity. Plotted here is the electrode potential versus logarithm of the glucose concentration. First of all, we see a very high sensitivity of 80 millivolts per decade and a very high linearity over a wide range. 80 millivolt per decade sensitivity is exceptional. We have to look at the Nernst equation, which tells us that the thermodynamic theoretical limit in potentiometric sensing is 59 millivolt per decade. based on classical thermodynamics, fundamental. The quantum dot sensing electrode produces a sensitivity of 80 millivolts per decade, significantly beating the theoretical Nernst limit. Obviously, we have a quantum structure, so classical thermodynamic does not apply. Response time, important for the sensor. The sensor is very stable and very fast. Within 2 seconds, a stable response is achieved. On the contrary, the bare indium gallium nitride layer without quantum dots on top is unstable. So the quantum dots produce a stable response, very fast, and with a super-Nernstian sensitivity. Reusability, here is a cell potential measured over 10 consecutive days, and we see there is very limited fluctuation. So the sensor shows very good reusability. And also selectivity. If we add uric acid or ascorbic acid, the signal is not much disturbed. Well, this is not an effect of the quantum dots. This is an effect of the glucose oxidase enzyme, which is just selective to the oxidation of glucose. So the selectivity is a matter of the functionalization and not of the quantum dots. We also made cholesterol biosensors. Again, the potentiometric sensing setup. Biofunctionalization is now by cholesterol oxidase to selectively oxidize cholesterol. The sensor performance is shown here. Again, very wide linear range with a sensitivity which now exceeds 95 millivolts per decade. So we approach almost twice the theoretical Nernst limit now. Again, the response is very fast. We compare here with a planar indium nitride layer, which has a sensitivity below the Nernst limit and less fast response. The indium gallium nitride layer, again, not stable, and also the cholesterol oxidase leads to a very high sensor selectivity. Reusability, again, very good. The temperature dependence, which has been measured for this sensor, is fine up to 50 degrees C. Then the sensitivity drops. Now, again, the superiority of the indium nitride quantum dots for potentiometric sensing. And the explanation is the same as before. It relies on the positively charged intrinsic surface donor states on the indium nitride surface, which are partially unscreened by electrons because not enough electrons can enter the quantum dot due to the Pauli exclusion principle. Electrons are partially expelled to the indium gallium nitride layer underneath, forming a strong electric dipole, leading to strong attraction of electrons, which in this case catalyzes the oxidation of glucose. So it's fundamental. The quantum dots act as a catalyst for oxidation, applied to water splitting for the generation of hydrogen, and applied to biosensors for the oxidation of glucose or cholesterol. The super-Nernstian sensitivity originates from this charge partition, from these quantum mechanical charge partitions of electrons partially inside the quantum dots and electrons partially expelled to the indium gallium nitride underneath. Finally, I would like to show you an all-solid state indium gallium nitride quantum dot sensor. We have found that if we grow thick indium gallium nitride layers with indium nitride quantum dots on top, we get a sensing electrode with a very high sensitivity. If we grow a thinner indium gallium nitride layer, the morphology changes. And if we grow indium nitride submonolayers, so partial monolayers, we can produce a reference electrode which basically does not show response to analyte concentrations. So it provides a stable reference potential, what a reference electron should do. This is due to charge engineering of the surface. If we have the right surface morphology, and if we deposit submonolayer indium nitride, with the positively charged surface donors, and also taking advantage of the morphology, which produces negatively charged n-plane sidewalls, we can create a charge-balanced surface which at the end does not show any response to analytes. Here are the data of this sensor. First, we measure the sensing electrode versus the silver-silver chloride electrode. The quantum dot sensing electrode again shows super-Nernstian sensitivity, 79 millivolts per decade in this case. Then the reference electrode, which has a sensitivity of only 2 millivolts per decade. As acceptable tolerance is 5 millivolts per decade for a reference electrode. So we are very well within accepted tolerances. And on the right side, the all indium nitride solid state sensor with an indium gallium nitride quantum dot sensing electrode and an indium gallium nitride submonolayer indium nitride reference electrode. The advantage is, with this sensor, we can easily make it very small. It is very robust and compact because we do not need these very inconvenient liquid-filled silver-silver chloride reference electrodes. No maintenance is required, and it's very easy to use. Stability and drift and reusability. Long-time stability, very good. A drift, less than 1 millivolts per hour, 0.17 millivolts per hour for this sensor. And also the reusability over several days fluctuates very few. So again, this all solid-state sensor constructed from the indium gallium nitride solid-state sensing and reference electrode shows all desirable properties. And with this, I would like to thank you for your attention.